everyone, how are we doing? I've got the background up. Where we are, here we go. There we go. There we go. Let's see. We had some questions about assignment 1 project or part 1. I feel like my video is a little jittery. So many things. We had 1 buffer yesterday. We can take 1 buffer though. 1 buffer is not going to destroy everything. There I am watching my own video. We're going to pull up assignment 11 right here. Let's see, which part, Roderick, were you wondering about with assignment 11, part 1? Let's get assignment 11 right here and part 1. And which part were you wondering about with it? Let's take a look. Okay, got it up and ready to go. Let's see here. Good. Oh, Olivia, let me see. Is Mubot on? He is not on yet. Let me turn him back on. I thought he was on. So, and how's the I think our class, yesterday's class is over 90%. So we've done it. We are 90% last I looked. I'm reloading it now. Hopefully I'm still logged in. My phone's out in the main room. 38, 33, 71, 90%. Don't tell everyone. We've done it though. We've got 90%, which I think was our goal. Let's see if we can break 95, which would be even more amazing. Mubot is on. Let's get those points in. So good to see you here, Cliff. Yeah, yesterday's class. We got to get today's class up though. All classes. Let's put out 100 points right there. And which part were you wondering about? Let's hop over to the main screen right here. My neighbors are like, there we go. What are the neighbors doing? Let's hop over to the main screen. The misclassification, the reminder. Yep. And the reminder of the meaning of the misclassification rate. Yeah, let's talk about it. So which one are you wondering about for like a specific model? I might already have some models up. So when it comes to the misclassification rate, so let's talk about the misclassification rate a little bit right here. So once you've made a model, explain the interaction. We've done a lot of that. So you're talking about the misclassification rate. To compute the misclassification rate, and let's talk about misclassification rate a little bit right here. You need to use a confusion matrix. So confusion matrix. I don't know how to spell confusion matrix. Does this say, hey, there we go. So here's a confusion matrix right here. So when it comes to the misclassification rate, you're looking at people who were predicted incorrectly. So people who are predicted incorrectly in this instance would be somebody who is what, but what. So when it comes to misclassification, Roderick, what do we have right here? Yep. Part 1 and 5. We can go back to part 1 here in a moment. So how are people misclassified here? Can you explain to me how somebody is misclassified according to this model? So kind of look at how the model makes predictions, and then how somebody would be misclassified right here in this model. Like, what is the misclassification rate? How many are misclassified? So that's the kind of thing to understand with this right here. Like, how many were so first you could maybe say, like, how many were misclassified? What does it mean to be misclassified? Like, the model does this, but you're actually this. So what does it mean? Predicted as male, but you're actually, exactly, that's what a misclassification is. So the model is classifying people, and it says these 350 people are female, and they are actually female. So this would be a actual correct classification. But these individuals right here were predicted female, 43 for the male, and exactly, these are people who are male. Well, the 43 is predicted female. Does that make sense right here? These 43 are predicted female. And then, got something in my teeth. There you go. Sorry, everyone. These 43 are people who are predicted female who are actually male. These 43 are people who predicted female. Does that make sense right here? How you go up, down like this. So you can see predicted female. They're over this right here. Predicted, their actual male right here. So actual male, predicted female, these 43 individuals right here. And so, hey, what's up, Maddie? Good to see you here. Feel free to ask some questions. We'll probably start doing some 201 here in a little bit, but we're doing 320 right now. Yay! And so, how many people total are misclassified? What did I ask? What is the misclassification rate? Not yet. Which one do you want to do? Which one do you want to talk about? We can do that after this. I think we're going to do number 1 on this also, but feel free to ask. Yep. So you want to divide by the total right here to get... You want to go You could you could probably take, and there's that. You could do that. You could add together the percentages right there. what was it? And then it's got the totals, but yeah, I wouldn't do that right there. That's getting you the percentage in each group, but you can get this right here, and that's the misclassification rate of the model. And then trying to think what else you asked about. So then, hey Mubarak, good to see you here. And the first one, explain how the naive model predicts the quality. So you can actually get the naive model from this. So how does the naive model make predictions? So the table shows the entire result. Yes, let's do that next. So how do you get the naive? What is the naive model and how does it make predictions in logistic? I'll put a cut in the video. So talk about misclassification. Okay, let's talk about the naive model and how does the naive model make predictions? So how does the naive model make predictions? How does the naive model make predictions? Oh, Lauren. Sorry, Lauren, I didn't see you there. And Amelia, sorry. Oh, Amelia's thing is red. That's, I think, why I missed it. After the question, go over the chapter 19 chi-squared with gender and political party. Yeah, Amelia, let's do that next because your question came first. Sorry, Amelia, I didn't see that. I don't know, man. I need more coffee. I need more coffee. So, and good to see everyone. Good to see Lauren and Amelia. Feel bad when I don't say hey to someone. It's UT is like talking about they want. I think UT is like we can't have as much online. We have too much online. And I'm like, no, our class works online. And I forget to say hey to people. And I feel bad. Well, the naive has nothing to do with interactions. Don't worry though. The naive is the model that has no what's in it. The naive. See, Maddie's like, hey friends. Maddie knows what's going on. Come in here. You say hey to your friends. People are here. We're just having a conversation. That's the way it works. I want this to be as good as in person. I don't know. I miss my in-person office hours, but I want this to like be a good substitute. Naive has no X's, which means it would have no interactions because there'd be no X's. So the naive, you could write a naive model by going, I'm just doing a summary. We're using this survey. And there's a naive model. Good to see you here, Parker. So there's the naive model right here. So with the naive model would predict everybody what? And it's not really even a model. Yeah, it's just the Y variable. That's all it is because it bases the predictions off the probability of the Y. So the naive, what would the naive model predict for everybody right here? How do you? What's the naive model going to predict for gender right there? How can we look at that? Good to see you, Cliff. How do we look at the summary and we figure out the naive model would do this? How can we look at the summary and be like, oh, the naive? Well, the model itself predicts the probability of somebody being male. That is correct. And for those who are wondering, like, why would the model predict the probability of somebody being male? And I think I still have that model that can be visualized. The model in logistic always predicts the probability of the last alphabetical. So the probability of male is what we're predicting. Hey, Brian, you bet. We're right about to do it, Parker. You bet. We got we got one from Amelia, and then we got one from Maddie. So we'll definitely be doing some chapter 19. So, but how does the naive model make predictions? The naive model, if you knew that the majority of people who took this survey were female, and I told you predict for a random person what they are. Well, this is basically the matrix right here. And look at these values right here. Do you see this 386 right here, and this 386 right here, and this 313 here, and this 313 here? So the naive model is actually right over here. This is the naive model. This is our model. I shouldn't say actual, but this is our model with the X's that makes predictions. And so these are the predictions from the model using the X's. And then the naive is over here because the naive doesn't actually use any of the X's to make predictions. So what would my model predict right here for somebody being male or female? And just think about how the naive makes predictions. It would say most people are female. So what would my model predict for everybody? My model would say most people are female. So how does the naive would say most people are female? So I guess what? If most people are female, the model would just say, well, then I guess I'll just say that everybody. What would it say? So the naive only knows that most people are female. It doesn't know any X's, like how height or weight explains somebody's gender. What would the naive do? So it would say about that. It wouldn't say 55% of people are female. It's going to say everybody's female, or everybody has a 55% probability of being female. It is true that 55% of people in this survey are female. Like that is true. that 55% of people in this survey, 55.22% of people, and it would be probability Y, but we're not going to say that 55.22% of people are female. We're going to say everybody is female. Does that make sense what the naive does? Is basically like uses the most likely thing to guess. It's just saying, well, most people are female. So if you talk to a random person, they're probably female. So I predict everybody's female. So what percent of the time would the naive be wrong? And so this is a good stats for one question. What percent of the time would the naive get the model wrong? What would be the misclassification rate of this naive? And it would actually be the probability it predicts for male, but we can just do the complement of this. And so that's the percent of the time the naive gets it wrong, which is actually the probability of somebody being male, which is also the probability the naive would predict. Explaining these things is like the important part of it. Like the naive would predict a probability of somebody being 44.77% probability of male. The naive is going to predict that everyone's female, though, because the non-level of interest has the higher probability than the level of interest. And thus, we would predict everyone is female, and we'd be right 55.22% of the time, and we misclassify 44.77% of people with the naive model. Does that all make sense, Roderick, as I say all that? Like how the naive makes predictions, what the naive will predict. The naive just looks at, hey, Adam, good to see you here. We just did some 320. If you have some more questions, we'll finish up some 320 right here. So I would say that the misclassification rate is going to be, it depends. It depends. It just, you can't always do it. You have to, the misclassification rate is going to be the non-majority level. So it just happens that this is not the level of interest right here. So watch out, because the naive can never misclassify more than what percent? The naive can never, this is a good theoretical question. The naive could never misclassify more than what percent? The worst misclassification rate according to the naive could be what? I think if you have two things and you do random chance, I mean, the worst misclassification rate according to the naive would be what? Because the naive will always pick the majority level. Like if you're trying to predict, does somebody live in Tennessee? Like who goes to UT? You'd probably predict yes, because the majority of people live in Tennessee. So the naive can never misclassify more than what percent? Exactly. Great job, Roderick. Yep, that's 100 points right there. That's a great answer. Yep. It can never misclassify more than 50% because it's always going to get the majority level right. So it's always going to get, does that make sense? How it's always going to get the majority level right. So don't worry about the level of interest, because it might just coincide that the naive gets the level of interest right. It's never going to be always 1 minus the level of interest. It's just, what is the majority level? The majority level here is female. So it says everyone is female. So it gets wrong males. But so males is the level of interest. So you can't look at and say, well, it's just coincidence. It has a 50-50 chance of being that the level of interest is the misclassified or not the misclassified. The naive always just uses the majority level to say most people are this, so everybody's this. This is nothing to do with level of interest. It's majority level. Does that make sense, Roderick? Like the naive doesn't really care about level of interest, even though the probability it puts out will be the level of interest, like when it makes predictions. If the naive made a prediction, it would predict everyone has a 44.77 probability of being male. And then you could find the probability of being female by doing 1 minus it. And so we can actually see the naive. I don't think I have. I'll make a naive of it. Evil. So here's the naive model. And here's the, oh, wait, I didn't do the naive. So here's the naive model, and here's the intercept, and that's all the naive makes for predictions. And guess what we get if we do e raised to the over 1 plus e raised to the, oops. There we go. We get that. And that looks a lot like that. So this right here, this is very important, knowing that this is a logistic, and we have to take this number and do e raised to the over 1 plus e raised to the, and then we get the probability of being male, which according to the naive is a static probability that just stays the same, but I think it's got it. Does that make sense, Roderick? This is the e raised to the, do you understand what I did right here with the e raised to the over the 1 plus e raised to the? That's our regression equation. That's e raised to the over 1 That'll be very important for the test. Have a calculator that can do E also. We'll see if there's some more questions. Let's go to space. I don't think I have music on. I do have music on. I have music on. Music. Awesome. A little bit of music. So many things. Man, I can't believe it's almost summer. I cannot believe it. It's absolutely crazy. It's like a new thing every day. I'm like, it's so crazy. Roderick, I might be flying in. You're welcome, Roderick. And everyone's like, Brian, you have to fly into Knoxville. UT is definitely like, we need every class to have an in-person component. And I was like, I've been teaching online for forever. I don't know. It's interesting. So I'll go do the homework. 201, we're loading up your work right now. But I hope everyone's enjoyed our class. I was replying to emails this morning. Thank goodness, Cliff says, for 201 or for which thing, Cliff? I don't know which, thank goodness. Let's see right here. Head over here, do some 201. Let's do this. Summer, I know, thank goodness for summer. I know, well, I want to fly in with Chelsea. I want to be like, Chelsea, let's go spend a weekend in Knoxville. You see, she could fly in for the weekend, and I could stay for like a week. Oh, no, you're fine, Cliff, you're fine. Let's throw out some 50 points. Don't worry, Cliff. I was like, which thing? So that's the interesting thing about online is like, if you say thank goodness, the second project bumped my grade up a whole letter. That is awesome, Maddie. I kept telling people, do the project early. I said, was Brian right? Do the project early, get a 107 or get above a 100. So great job, Maddie. Congratulations. That's what I was telling everybody. Like, that was my advice. I was like, do the project early. Do the project early. And Maddie, if I like to have students come and speak to other students, if you want to speak to other students, which I think 320 had students come and speak to them. So sometimes I've had 201 students come and speak. You know what's so funny? Is I hit this cycle of Kyle, that's his name. His name's Kyle. I miss Kyle. I miss seeing like a bunch of my students. But Kyle was in a class where a student came and spoke to him. And then I don't know if Kyle ever spoke to a class, but I'd have Kyle come and speak to a class. But Kyle, it's just funny. Like he was in that class. And I remember him coming through the door, and I had a student with me, and I was like, oh, so-and-so is going to come in to speak. And I don't remember the student who came and spoke to them. I just can't think of them right now. But Kyle was in the group of students who was spoken to, like that the former student came and spoke to them, and now Kyle's a student. I'm like, oh, I should get Kyle in here. Let's remember that day. Can we do question 4? You bet. Let's do that one to start, Kaylin, right here. Let's do a bunch of the homework. Let's do that. Let's get serious. Homework time. Congratulations, Maddie. All the positivity in the chat right there. Thank you, everybody. Okay, we got Democrat and Republicans and independents right here. Ma Pearson trying to get political. Avery says, yes, please, number 4. Let's do this. So here we are. We are doing the chi-squared test of independence. We're not doing some homogeneity. So right here, homogeneity, I haven't really done much of. It's to see if everything comes from one group, really. Chi-squared test of independence is something we do, but not the homogeneity. It's just what this material covers. And so let's go right here and copy this data to the clipboard. This is much longer if you do this by hand. I would not suggest doing it by hand. We're just going to copy this to the clipboard, hit Command or Control C, and there we go. And then go over here. And I have a jump data sheet open right now. We need to make it look like this. So let's go here to File, New, and I'm going to go very slowly, Data Table. File, New, Data Table. Now we're going to full screen this. We're going to go to Edit, Paste with Column Names. Paste with column names. So you need to make it look like this. Once again, do not make it look like this. If it looks like this, no. If it looks like this, yes. Don't do this. Don't do this. So right here, we have it the way it should look with a red, blue, blue, blue. So what we have right here is a table of data, but this is still not correct. And this is where you have to know this extra step to make your life a lot easier, is go to Tables, and then go to Stack. Tables, Stack. We're one step away from getting it into Jump. So now we're going to double click, and everything is over here except for the red column. So double check your screen, just pausing right here so everyone can be on the same spot. Maybe you can pause the video live, but this will make our life way easier and analyze all the data for us. We'll go ahead and click OK. Now, this is the way it should look. If you look at the data sheet I first had open, looks a lot like it. And this is the best way to get the data into JUMP, where you have two categorical variables right here. One categorical variable, another categorical variable, and the counts of the observations. This is why we call it count data, because it's just how many people were in the online class who passed, how many people were in the in-person class who passed. This was fake data we made up yesterday. How many people were male and Democrats? 31. How many people were male and Republicans? 47. So all of this, nice and easy to look at. So let's go back to our data right here, which is correctly created. Only this one should be blue because that's the quantitative one. And let's go to Analyze Fit Y by X. Analyze Fit Y by X. And now with Analyze Fit Y by X, we're going to go ahead and put this right here is political party. We could have labeled it, but this is political party. I don't know why they have the dash. And then let's go here and put label right here. We're going to have, sorry, that is gender. And then the other one's political party. And then this needs to go right here. This is the mistake people usually make. I've seen a lot of people do this problem. Usually they forget to put data right here because we need the data right here to do it. That's the mistake I usually see people make. So let's go ahead. We've got that we're predicting someone's label from their gender. And let's do it. There we go. We pretty much have everything we need right now. We'll go ahead and take a look at this, but let's bring the question back up. What is the appropriate null hypothesis? I don't want you to really look at these answers. This one does it perfectly. What do we just put here between gender and political party? And I'm going to fix it. What is the only word we put between gender and political party? What is the only word we put between gender and political party? So we go here, gender and political party. What is the only word? This one actually does it the way I want it to. And so you should know this trick. This is a very important trick for this chapter. The only word we put between gender and political party is what? So if I go, what is the only word Brian's going to write between these two? It's a very important trick we should know. I'm going to only write one word between them. What word is Brian going to write between these? I need someone to help out and say, what word with the chi-squared test of independence? Kind of. For this one, we won't use mathematical notation. This is the only one that breaks the trend of mathematical notation for the chi-squared test of independence. And so when we do the chi-squared, Maddie, good guess right there, 50 points. So for the chi-squared test of independence, what is the only word we add between them? For the chi-squared test of independence, what is the only word we add between them? So we only had one word between them. What is the only word we're going to say, like, this isn't something of this. This is, and then we can do the not of it. So we just had one word between them. Starts with an I. Just think about what test we're doing. Exactly, independent. So we want to say that, like, somebody's gender. Great job, Amelia, right there. We're just going to say they're independent, which means they don't impact each other. But look at this. Males were more like, can you see maybe that males were more likely to be Republican and females were more likely to be Democrat? I should have used the other colors. According to this, just, 50% of females were Democrat and 50% of males were Republican. It's somewhere in that neighborhood. But so maybe there's not independence to these. So the null hypothesis, my favorite way to write it, there's a lot of ways to write it, is that the two are independent of each other. That political party is independent of someone's gender, political party is not independent of someone's gender. So just be careful because they can change it. Sometimes they can say is associated and stuff like that. So you should understand what it means. Independent means they don't influence each other. Like if you know someone's gender, you'd have no idea what their political party is. The R being blue. I could maybe fix that. Let me see if I can fix that really, really quick. We should. Oh, look at this. Look at that. There you go. I know. We have fixed it. So now males are more likely to be Republican. There we go. That's just a little practice. And you can see right here if you hover over it. So, hey, good to see you here, Maddie. Or it's good Mary here. Yep. See, so hard with the like very similar names. 47% and then 52%. This is a nice thing is you can like hover over and get the percentages. Much more satisfying. There we go. It's like one of those things like oddly satisfying things or things like that. Like just helps out with this right here. So good to see you here, Brooke. And now we've got here, are the conditions met? Is this count data? Who can explain to me they're both what? So is this count data? They are both what? So is this count data? Like, what does it mean for it to be count data? Count data means they're both what? Like, this is, usually I call this condition number 4 right here. So is this count data? Here's a big hint. If we're doing this chapter, it has to be count data. And count data means that they're both categorical. So since they're both categorical, since gender is categorical, and like what do I mean by categorical? Like it puts it into groups. So yeah, great job, Lauren, right there. It has to be like if you're doing this chapter. Is it random? Sure. My Pearson, you should really state that they're random. You should say that they're randomly selected. Is expected cell count. Now, expected cell count. Let's see if we can compute an expected cell count right here. This is very important for the test. I'm going to go down here and make this just a smaller table. And let's find out how to get the expected cell count. Good to see you here, Galen. What would be the smallest? Now, be careful. Which would be the smallest expected group? Now, be very careful. Here, now, let me put it on a new sheet. Which would be the smallest expected group? Who can tell me where the smallest expected group is? And let's look at this. Where would the smallest expected group be? Which one of these is the, be careful, the smallest expected group? And I really like this question. This would be a decent, just straight question on the test. I wish I could have a click thing, like click on the smallest expected group. Be careful, these are the counts. These are not the expecteds. That's what don't worry, Lauren, that's exactly, and Maddie, don't worry. That's the smallest count. But remember how we do the expected formula. That's why I kind of like this as a test question, because the formula for expected is row total times column total over grand total. So the small, and that's for expected, the smallest expected would be this one right here, because these are the smallest numbers, so it'd be male independent. Does that make sense, Kirsten? I think Kirsten saw it. Don't worry. That's why I paused and asked this, because I was like, that's a good, tricky question, because the smallest expected is going to be right here. So can anyone tell me, just solve for yourself for a moment, put it in the chat, how many males do we expect to be independent? According to this, how many males are we expecting to be independent? How many males would we expect to be independent? And this is the great thing about jump. I can solve it really quickly. How many males? So go ahead and solve this. You want to take 36 times 99 over 205. That's the formula, row total times column total over grand total. And notice how it like hones in on it. If you go across it right here, it crosses in on it. So you do the row total for something, the column total for something, and then that's right there, 17.39. Nice job right there, Lauren. That's probably correct. That sounds correct. So you can go right here and you can check. You can go to expecteds, and great job, Lauren, right there. 17.385, 17.39. This is just practice, because there's test questions very much like this. The more you do it, like I can just show you the answers, but if you're here practicing it, great job, Kirsten, then you're going to be able to do it on the test. Hopefully be like, oh, you just create the cross and you times it, and then you divide by the total, and there you go. There's the expected row total times column total over grand total, and you do get a formula sheet on the test. So it is all met. The answer is yes, but we're here to practice and make sure we understand how to do the work. So this one would be super tough without jump. This is where you don't want to solve it by hand. This is one of those things you don't solve by hand. You just go down here and you look at the chi-squared test of independence, 8.927. But something we should know is that 8.927 is the what of all these numbers right here. Do you see this 2.5, this 0.7 here? So what is Brian doing to all the cell chi-squareds to get this 8.9? And I'm going to try to just do 2 decimal adds on them. What all the cell chi-squareds, if you what them up, you will get the Pearson chi-squared. If you take all the cell chi-squareds and you what them up, you'll get the Pearson. I didn't do enough decimals on it. But if you take all the cell, if you add them up, it's the sum, this right here, this number right here is all of these numbers added together. To make that super clear, because this is a really good review of the chapter. Like in 10 minutes, we're reviewing the whole chapter almost. So if you take all of these numbers right here and you add them all up, you get this number here. So that's how that number is attained. Great job, Kaylin, right there. Let's throw some more 50 points out there. Everyone's practicing, following along. The Pearson chi-squared test statistic is the sum of all the cell chi-squareds. The Pearson chi-squared test statistic is the sum of all the cell chi-squareds. What then we have to do is we have to draw this out. And it looks like it would draw something like this right here on a chi-squared with 2 degrees of freedom. So that's a chi-squared with 2 degrees of freedom. It would be a very small probability. It'd be something like this. And that is the probability right here in the small tail side. Why is it a chi-squared with 2 degrees of freedom? Brian, this is a what by what? Be careful, don't use the total columns. Brian, this is a what by what? So we're doing the how to get the degrees of freedom right now. We're basically solving the rest of this because we'll be done with this question in a second. Brian, this is a what by what? So it's how to get degrees of freedom on this question. If you're watching right now, how to get degrees of freedom. You say, Brian, this is a 3 by 2 or 2 by 3 either way. And then you just reduce each finger down by 1 and you get 1 times 2. So you say, Brian, that's a 2 by 3, whichever way you solve it. Brian, that's 2 by 3. So then you reduce the fingers down and then you get 1 times 2. There are 2 degrees of freedom. And that's what we see right here. And we'll be practicing a lot more of this here in a moment. But does everyone, that's probably one of my favorite things to do. It's like, hey, that's a 2 by 3. Chelsea saw this and she's like, wait, that's how you do the degrees of freedom? That's how, like, that quickly? I'm like, yeah, you just say it's 2 by 3, reduce it down. There you go. It's 1 times 2. You got it. Degrees of freedom. And so we now have the degrees of freedom. We would have to go to an applet. We do have the chi-squared applet. So just so we can see this right here, when you obtain these numbers, MuBot's going to tell us about the chi-squared applet here in a second. If you were doing this by hand, you would have to take this number and go to the chi-squared applet. MuBot. Did I do a capital CHI? There we go, MuBot. MuBot is no longer banned in the chat. You have to go to a chi-squared with 2 degrees of freedom, and then you would put in the 8.92, and you would get the p-value right there. So that is how we're able to get the p-value using the chi-squared applet. But the good news is that JMP does all of this for us and gets us, this is down to a little more decimal place accuracy right here and gets us the p-value. So let's go ahead and finish off the question right here. Enter in the chi-squared test statistic, 8927. I've got it screenshotted. Once again, we're just going to use JMP. Yep, there we go. Enter in the p-value. Well, we just saw it, just in case you didn't notice it. The Pearson has your p-value. Remember, the Pearson has your p-value. There we go. And is the p-value below 0.05? The p-value is below 0.05. Reject the null. There is evidence for the alternative. So when you reject the null, there's evidence for the alternative, and that's got it. We reject the null, there's evidence for the alternative that there is an association or that they're not independent, that somebody's gender is not independent of their political party. It would give you information. So that's got it. I hope. Let's hop back here to space. Who feels like they understand the chi-squared a little bit better? It's going to take some practice of doing these problems. And which one do people want to do next? I'll do whichever one next. I think we had Epidural in the chat. We're just going to do all the homework. We can do all the homework first. So yeah, great job, Maddie. It's just practice. Like as we go through this next one here, be like, see if you can get the independence, not independence, like do the null, find out the conditions. Can we do number? Yeah, let's do number 1. Great job. Good to see you here, Jade. Let's do number 1 on the homework. You got it. Here we are with number 1 on the homework, the chi-squared test of independence. Once again, we don't do like the test of homogeneity. So it's not what we're doing. We're just doing the chi-squared test of independence. So hey, we're not doing the goodness of fit. And any of these tests are appropriate. Now we're doing the chi-squared test of independence. These data differ from other kind of data because they categorize subjects from a single group of 2. Oh yeah, so yeah, if you're doing certain tests, you have one group. A chi-squared test for independence is used here. Yeah, cool. So I don't. I was wondering what it said. I don't always read the comments. You're welcome, Kaylin. And then here we got Maddie's got one next. Let's do that. So okay. So what are we going to say right here? We have breastfeeding at 6 months and whether or not someone got an epidural are what of each other. What should we look for in the null? Which word when we do the chi-squared test of independence? I'm always thinking someone might be watching this video without seeing the other part of it. But when we do the chi-squared test of independence, we should always look for breastfeeding at 6 months is what of having an epidural. So breastfeeding at 6 months is what of having an epidural. So there should be a word we should see between them. I think they always do that for the null. They sometimes switch up the alternative. Like the alternative, yep, great job right there, Kirsten. Independent. So where do I see independent? There we go. There we go. And so obviously that eliminates this one. So now you don't see the is not independent, which I wish they did. And since it's a chi-squared test independent, we're saying like, to mean things are independent for the null is to say like this tells you nothing about this. Like, you're just saying these two things have nothing to do with each other. If you knew someone is breastfeeding at 6 months, that would tell you nothing about them having an epidural. You'd be like, they're just independent of each other. No information. By knowing this, you know nothing about the other one. So the alternative right here should mean that we know something. Like, the alternative would mean we should know something. Distribution of breastfeeding success is the same between the groups. That's a very specific, like, I mean, we would know something then, but actually that kind of sounds like a null. Breastfeeding success is independent. That's the null. Distribution of breastfeeding success is different between the groups. There's an association between breastfeeding success and having an epidural. So an association is what we're looking for right here. We're looking for evidence of the two, giving you information. So an association would be the alternative. We're not going to say that they are. I wish we just said not independent. Everyone got the hiccups all of a sudden. So there is an association. That is the alternative. Good to see you here, Lauren. And so there we go. Oh, is that it? Oh, awesome. Here, let's hop back to space. Which one? Students in an introductory statistics class were classified by birth order. Ooh, God, that's a big one right there. Let's go do that one. That one's on the quiz. Oh, wait. Okay, here it is. It's on the homework. Aha! Let's do it. Wrong button. There we go. Okay. You're welcome, Jade, anytime. Feel free to ask more questions anytime. So, oh, they show us the, whoa, holy mackerel. I haven't looked at this in a while. Did they actually give you there's the expected values. What do you notice about some of these expected values right here? Don't worry about the standardized residuals. You'll see at the very end, we're actually going to use this right here. We don't talk about standardized residuals. We'll be able to use the expected values right here. But what do you notice immediately about some of these expected values? Like this one right here, that is 3.12, 4.84, 4.84, 3.12. Something not good about these expected values. What do you immediately notice about these? Some are not greater than 5, which is the third condition, that all expected counts. And you might be wondering, how is this 3.12 obtained? Can anyone tell me mathematically how is 3.12 obtained? Like, can you tell me mathematically how they got 3.12? And so if you're thinking about that right now, hopefully put it in the chat, I'll show you. 3.12 is in this cell right here, which means it's this cell right here where 1 is. So I need to do 23 times 31 over 228. So we go 23 times 31. I did divide it by, I knew I did. 23 times 31 divided by 228, and that's that answer right there. So how are we doing this? This is just a good check. We're doing this by doing the row total times the column total over the grand total. And so this is just knowing how to get your expected cell counts when you just take right here and go row total, it's column total, grand total, and do this. And if you notice, the way this zeroes in on it is you're doing this group right here and this group right here, and it crosses in on this. So that's how we get the expected cell count, which is a row total times a column total over a grand total. And you have to do this for all of them. A lot of times the software does this for us. This is equal to the expected cell count right there. So it gives us a lot of this information, which is awesome. We're doing the chi-squared test of independence, not the homogeneity or the goodness of fit test. Oh, I didn't click it. I was like, what? There we go. And now we write out the null. Once again, what word goes here? I need to see it in the chat because everyone needs to know whenever you're writing out the null for the chi-squared independence. You're just going to talk about somebody's college that they're in and their birth order, and you're going to say the two things are what? Independent. Lauren was already ready right there. 50 points, Lauren, right there. We're going to look for not independent or something that would tell us that they are associated for the alternative. But the null is always you just put independent between these. So, oh my gosh. College choice of college is independent of birth order. Wow, that's crazy right there. So we just say college choice, like someone's college choice is independent of their birth order. Boom, just put independent between the two words, chi-squared test of independence. The alternative right here, there is an association. So that's what it means to not be independent, is that the two things are associated. They tell you something. So we should get that right. Yay, I was a little worried. So many choices. I was worried for the second one. I was like, did I read all the choices? I was like, look, yeah, that's what I'd say. So they have here 5 conditions. Let me point out, they sometimes break apart the randomization and independence condition. If things are independent, I usually just say they're random because they don't give you information about each other. So they broke those apart. Condition 1 right there is those two. So condition 1, random. So We have here the randomization condition. Condition 2, less than 10%. Condition 3, we got to pause though. Condition 3 is that we're dealing with the expected cell counts are greater than 5, which we're not going to check that one, but we do have count data because both variables are categorical. So condition 4 right here is count data. Both variables are categorical. And just in case you were wondering, we did see that expected cell counts were not greater than 5. That's really hard to see right there. Those numbers are blurring together. 3.127 or 1, yeah. It's hard to see. So we do not meet the expected cell count condition. So, oh, we did. So, well, we are checking it, but it doesn't meet the condition. It's very hard to see. Yeah. And so we can check right here ourselves. This cell right here, here, I'll show you. What is the expected cell count? So you should be able to compute this. The expected cell count for that cell is actually the same as the other one we just did, and it's not greater than 5. 23 times 31 divided by 228. And it's the same as the other one because this right here is the same 23. I wish I could just move that one thing. But that's not greater than 5. So we don't meet the condition right there. We don't have at least 5 expected cell counts. How many degrees of freedom? Who can do the degrees of freedom right here? Who can do the degrees of freedom? Brian, this is a what by what? The degrees of freedom are what by what? And then you have to solve it. You have to it. So who's got the degrees of freedom? I love these questions on the test. 9, boom. Brian, this is a 4 by 4, 3 times 3. That's all we're doing. Brian, this is a 4 by 4. What do we mean by 4 by 4? Don't count the totals. Sometimes people do that by mistake. You want to look at 1, 2, 3, 4 groups. 1, 2, 3, 4 groups. 4 by 4, 3 times 3, 9. Who would love it if there's some, like, just say me or yes in the chat, if you'd love it if there's a degrees of freedom question on the test like that, where it's like, what are the degrees of freedom for this? Exactly, Charlie. Charlie knows the equations. Charlie, a random Charlie appears in the chat. 100 points right there. Charlie, so good to see you. Charlie took 201 last semester, right, Charlie? I tell people, like, hey, just swing by, say hey. And, like, I'm so glad people remember some of the stuff right here. Like, Charlie's like, yeah, rows minus 1 times columns minus 1. Boom. Equations in the chat. So we see right here we have a chi-squared of 27.07. It gives us a p-value of this. We can show this visually right here. You don't have to do this. But since there's 9 degrees of freedom, 27.07 right there. Yep. So good to see you, Charlie. And there's the p-value going off the side of the screen, which we don't get all the decimals for, but assuming a significance level of 0.05. So do we reject the null or fail to reject the null? So the p-value is this. When the p-value is low, something the null. When the p-value is low, like, this is the good thing about this third test is if you get these things down, you look at that p-value and you're like, boom, Kirsten's just like, reject the null, Brian. So that means there is not evidence. Is there not evidence or is there evidence? Yeah, great. You're in 320 right now, Charlie? I'm trying to remember. I think if you are, you're not in my section unless you might be taking it very soon. We reject the null, and that means there is or is not evidence for the alternative. So I think you're saying, I don't think the null is true. I don't think the null is true. There is evidence. Perfect, Lauren. That means there is evidence for the alternative. Yep. I think this last part here is about the issue. So examine the standardized residual. So this really gets to, this is why this is included on here. Some of the cells with expected cell counts less than 5 have large. So it's really about those right there. So the reason, like, this is, oh, awesome, Charlie. Are you taking it in my section? If so, that's awesome. Like, if not, that's awesome. That's fine too. But Charlie, you're a great student. So if you're my student again, that'd be awesome. Some cells with expected cell counts less than 5 have large standardized residuals. So we're really just trying to go to this right here. We don't talk about standardized residuals in our class for this, but the issue is about the small cell counts, the expected cell counts. Well, I think you know what we should do. So we should finish off that last question. We've got one more homework question. We'll have done all the homework questions. Let's do it. Let me get it up on the screen right here. Oh, man, it starts off with something. Here we are. What are the degrees of freedom on this? What are the degrees of freedom on this? That's all right, Charlie. Charlie, you can swing by any office hours, anytime. You know I'm here. We'll all be unified. All sections will be working together. I'm going to be working on that with a plan with all the groups. So, you know, I'll be 100% here. So you can swing by anytime, Charlie. You can, there's 1 degree of freedom. Lauren, you're exactly right. It's a 2x2. That's sorry. 2x2. So it's a 2x2, Matt. Does that make sense why there's a 2x2 right here? Yes, no is 2. Yes, no is 2. 2x2. 1 times 1. 1 degree of freedom. So thank you. Tell UT. I think UT is like, we can't have as much online. I think we saw the pendulum swing towards online, and now it's swinging back a little bit. And I'm like, no. We work hard at our online classes. The smallest expected cell count. Okay. So which of these, is it a yes, yes, or no, no group? Let me see. Okay. I want to B yes or B no, E yes or E no. Like here's a combination. I'm gonna put this in the chat. Like B, I put B yes, E yes. That's gonna be this group right here. Which of these groups would have the smallest expected cell count? Which of these groups would have the smallest expected cell count? See if you can solve that in the chat right now. Look for which group. So I'm what I put in the chat right here. Up. I think Maddie's done it. Maddie, you are correct. It'd be this one. Basically, you take the smallest column total and you take the smallest row total, and that's the smallest expected cell count, because the top of the equation, you know, you're always dividing by the same amount. Do you need to find it? You don't need to find exactly, Lauren. You don't need to find it for every one. You can just go to the smallest column total and the smallest row total, and then you've actually checked. Because imagine this. I forgot to use this example in both classes. Bar with your friends, and the youngest person is 22. Can everyone go to the bar? So if you go out to the bar with your friends and the youngest person is 22, can everyone go out to the bar? So it's like a logic problem. You're going out to the bar with your friends and the youngest person is 22. Can everyone go to the bar? Yep. And so we're going to check the smallest expected cell count here to see if it passes. And if the smallest one passes, they all pass. Does that make sense? Like what I'm using here? Like if this one is greater than 5, they're all greater than 5. No, YouTube, you don't buffer on us today. We buffered yesterday and we got our buffers out of the way. We got all the buffers out of the way yesterday. Oh no, tell me everyone if it's working. Are we back? How are we doing? Let me look to see if I see it on my side. It might be a UT. You're back now? Okay, good. I don't see. I can see like stuff on my side. Jade, did you have any buffers? Everyone's saying it's better now. It's hard to... I've been trying to narrow down if it's like UT or if it's... So... Jade, if you're right, we're back. Awesome, good. Sorry, it's so weird. It happens so infrequent. It happens like once every 45 minutes, which is not good. I don't like that. So I was in a Zoom meeting yesterday. I did. Okay, good. Thank you for telling me, Jade. It looks like everyone buffered, and I don't know. We got to do a shout out every time we buffer. We got to put this out. So if you're watching this video later, I'm going to put this in the chat right here. We've got like 4 likes on it. I think we got to get more than 4 likes to have Elon Musk. Even I liked it. 6 likes. my Twitter game is pretty weak, but I don't know. We might go to Starlink. So maybe, man, if Starlink could just like, I don't know. Hopefully, maybe see this, but check that out. Yeah, I think it's Suddenlink. I really do. Just so everyone can see, if you're wondering, Suddenlink. Here are the reviews. I have gig speed internet. And they've got all these commercials like, you're getting the gig speed. And they're like all happy and stuff. There's the reviews of my internet provider. 1.4 stars. That's not a good internet provider. It's the only one we got. It's the only one we got. Could you do chapter 19 quiz about the war injuries? Yeah, we do it next year, Carly. You got it. Good to hear, Maddie. Could you review how you got part B again? For part B, we have to take the smallest. So what numbers are we multiplying together? Hey, let's show how to do this. Yeah, it's a bummer. Like I can't get another internet provider, which is just so stupid. I should call like, I don't know. One, Mary, just one. Just no homework, just one quiz. Just one quiz. So the formula is row total times column total over grand total. And so row total, it's an R, times column total over grand total, and that is equal to the expected. Does that make sense right here? Mm-hmm. And so Lawrence put in the chat, and then you have to notice how this crosses in on it. So that's the one we're doing right there. It doesn't truly matter which one we're doing. Great question, Mary. And so we're getting the expected cell count for the smallest one. So we took the smallest row. I think other people were asking, like, which one are you doing? And we're doing just the smallest. So we're taking this as the smallest row. This is the smallest column. And then we were able to get this right here. And just to show the mathematics on this again, we just go right here and we go 386 times 445 divided by this right here. And there it is right there. To do it correctly. Sure. Okay. Something went wrong the other time, but that's correct. We already got it correct right there. Boom. Okay. So they break apart the randomization independence condition. Congratulations, Maddie. Good to hear that. We got a great job on all the art. I wish I was a much better artist. I really do. Chelsea made me, wish I could take it off the wall and show it. She made me a piece of art for our 9-year anniversary. And it's really nice. She's a great artist. And so now the next, we passed the expected cell count. Why do we pass the expected cell count, everybody? Expected cell count, it's on the wall. She's like, why is the art off the wall? I'll be like, I took it down to show the class. I'll try to take a picture of it and post it. I wonder if maybe I should, I don't know, I can start tweeting these things. Like, yeah. Count data means they're both categorical and less than 10% of all selected. So less than 10% of all individuals, all of them are met. Yep, totally. And always make sure to practice your conditions. Oh, we just completed the homework. That's awesome. Let's do the war injury one now. We just got the whole homework done. We took our final pictures, so when they get uploaded, I'll send them to you. Awesome. I'm excited to check this out. So that's the homework. Homework is done. Awesome. Let's go check out the quiz. We got the war injury one. I need to pause my video. 27 people watching. If you're lurking in the chat right now, say hey. I just saw we got 27 people watching. What? Who here would like for me to dress up as the Joker for some of our final reviews? Because I'm just like, I was like, if I'm going to be reviewing, because I might do like a 4 or 5 hour review, like maybe do 2 hours for 201, 2 hours for 320. I was like, it'd be more fun to do it as the Joker. And I'm just like, why not? Why not do something fun? Like, I don't know. I got to make sure I have enough makeup. So shout out in the chat if you're here right now. I'm loading up the war injury one. We've done a lot of questions. Let's see who's in the chat. Maybe we got someone to talk. Someone in the chat say hey, who's not. Josephine, so good to see you, Josephine. Let's do it, Jade says. Mary's in the chat. Do it, says Lauren right there. Adam, good to see you. Adam, Mubarak. So good to see everyone in the chat right there. 27, that's just so crazy to me. Awesome. Let's do this. Let's hop over here to the war injuries. Okay, stretching out. Here we go. War injury problem. A certain story describing, we gotta do like a certain story describing several weeks of a long war, including many details of injuries and outcomes. The accompanying table summarizes 147 recorded injuries, for which both injury and site and outcome are provided for the story. Are some kinds of injuries more lethal than others? Complete parts A through E. Have you done the chapter 9? Oh, we did all the homework, Adam. Yep. Now we're doing the quiz right here, knocking out some of those questions. You got it. Yeah, awesome. Mary, you can rewind these videos live. So you can rewind and find the question. Be like, let me just go backwards in time right here. Can't do that on Zoom. So we got here body, head, neck, limb, fatal or not fatal. Okay, good. I was like, it makes more sense to me if you get injured in these areas, it's going to be more likely to be fatal. But if you get injured in the limb, less likely to be fatal right there. So these are the more fatal injuries are to your body, which I guess might be the chest. And if you get injured in the head or the neck, that's not a good place to get injured. The limbs, not still good getting injured. After I go to rewind, how did the homework? See, Maddie? Good to see you. What is the one word we put between the null and the alternative? I mean, the one word we put between this. We say like where someone gets injured and it being lethal are what of each other. I just want you to think about this for a second. So what's the one word we put between it? Everyone should know when we do the chi-squared test of independence, what's the one word we put between it? Independent right there. Lauren knows, like, boom, independent. We just say this is independent of this. And I love it because now they're going to say they're not independent. So we have it. Okay, it's a quiz, so we can't do them all. So that's the null right there. We just say where you get injured is independent of if you die. Now, this one is much longer if you do it by hand. To do this by hand, you'd have to go here and you'd have to do each individual one. So you can do this if you really want a lot of practice, is you can go right here and you can take 115 times 62, that's row total times column total, this one times this one, over 147. We get 48.50. So you can do them all by hand like that. This times this over this times this over this. But I'm going to go ahead and take it and put it into Jump, copy to clipboard. We're going to hit copy right here. And so we've brought it. Now we're going to go into Jump and go to File, New Data Table. You can do Controller Command N also. So now within inside of Jump, we're going to go ahead and go to Edit. And this is very important. This is very important. This one you have to paste with column names. Very important. You'll notice it's correct if you see red, blue, and blue. It is not correct if you see this. So if you see this, start over and make sure you paste with column names. One of the most common errors is the data does not get pasted in correctly. So now you're going to go to Table and go to Stack. If it looks like this, you have it correct. So we're going to stack fatal and not fatal right here. And then we're going to go ahead and click OK. And then we're just going to go to Analyze, Fit Y by X, Analyze, Fit Y by X. And now we're going to put the column right here, which is where someone got hurt. Then we're going to put the label of what happened to them. And then we're going to put the data right here. So does the site of injury, which we could have called this site of injury, give us information about whether or not it's fatal, which is the label. And we need this is so important. You need the data right here or they'll all look even. You should see differences like we saw where people who were hurt in the limb were less likely to get a fatal injury. Here's the fatal injuries. So now let's go right here and remove out everything. Your counts should look like what you had in the previous table. So here's all the counts right here. Now you need to go and click expecteds, and we're going to take a picture of this. So there's the expecteds, and this is going to help us out this question. There's the expected counts right there. We did one of the expected counts by hand. So let's go look at that expected we did by hand to make sure we did it properly. Ooh, that's where Brian misclicks and changes something. Sorry, I clicked away and changed my answer. So we did the first one right here, the 48.50. So we did that one by hand and got it correct. So the next one is head neck, and good to see here, Carson, 35.20. And then the next one is limb fatal, 31.29. And I do suggest trying a few of these by hand, 13.50. And it's very easy to make errors. 9.80. Make sure I don't miss anything in chat. And then the last one right here, 8.71. There we go. I think I've got those all correct. The chi-square test statistic, I would not compute this by hand. We've never had everyone compute it all by hand. I mean, we could. What we could give you, let's pretend we write a test question here, and let's do the following. Who here could compute the chi-squared test statistic by hand right now for me? What if a test question said, and this was worth 10 points, who would like this test question? It said, compute the chi-squared test statistic by hand. So who could compute? It is given to you on this answer right now. Who here could compute the chi-squared test statistic by hand, and who can explain it? What would you do with all these values right here? Which this is a really good review. We're doing basically all the steps. What would you do with all these values, like with that 0.8, that 3.12, which these are the cell chi-squareds obtained from the observed minus expected squared over the expected. That's how all those values right there are obtained. They're each of their observed minus each of their expecteds, respectively. So you have to take and solve each of those to get each cell chi-squared. And then what do we do with all those numbers to get the chi-squared test statistic down here, which is the Pearson? The Pearson has your p-value. You add them all up. Great job, Kirsten. That's the sum of all the cell chi-squared statistics is the Pearson chi-squared test statistic. So these are cell chi-squareds, and this is the Pearson chi-squared test statistic. So that's got it. So 41.92. Yep, 41.92. Brian, this is a what by what table. So look at how many groups there are. Brian, this is a what by what table. Be careful, don't add up the totals. There's not totals on this one. But sometimes, or I'll put it over here on the side, sometimes you are given the totals. So So you have to watch out. Like you could see a table that looks like this. These are both the same thing. It's a 2 by 3. So how many degrees of freedom are there? Which the answer is on the screen also. It's a 2 by 3. So you reduce by 1, and there's your equation. So it's a, and so how many degrees of freedom? And the answer is on the screen. 2 degrees of freedom. Yep. There are 2 degrees of freedom. Because it's a 2 by 3, so you reduce the fingers down 1 by 1, and you get 1 times 2. So 2 by 3, 1 times 2, 2 degrees of freedom. Great job. Great practice, everyone. The p-value here is 0. I believe it was, right? Yep, it's 0. Just if you hover over and jump, it'll show you it's ridiculously small. It'll be like it has so many zeros. You can hover over it. It should show you it. Come on, jump. There we go. Oh my gosh. It's got 9 zeros. It's ridiculously tiny. So what should we conclude? What are we going to do to the null? What are we going to do to the null? Who knows what we're going to do to the null? It should be like super obvious. We're going to what the null right here. Great job, Carson. Let's throw some 100 points. Got a bunch of people watching. We're going to what the null. The p-value is low. We're going to what the null, and that means we have what for the alternative. We're going to reject the null at the 0.05 level of significance, and that means we conclude that they are not independent, which is the alternative. The alternative we have evidence for. They are not independent. Just making sure I didn't mistype anything. Let's cross our fingers. You always got to cross your fingers. Not today, my Pearson. Not today, my Pearson. We don't type numbers in the wrong way. We get everything correct. Get all those 100s today. Okay, should we do the other one? Good to see you here, Caroline. Awesome. Was there another one people were really wondering about? I'm just going to keep doing all the quiz questions. So hopefully we can do them all. There's another injury one with site of injury and stuff. It's very similar. I know I love those Mu Bucks too. We have to reset them between semesters. No. My question has body. Yep. Okay, let's do that one. You ready? So let's do this one right here, Carly. The other question. Here we go. I've got it on the screen right here. And so once again, I need to know that word we use for the chi-squared test of independence to make things nice and easy. What do we use between the two things when we talk about where somebody is injured or the weapon in the injury site? Take an arrow. You see, if they were going for memes, they would have knee right here, and they'd have one dude right here who took an arrow to the knee. If my Pearson just was self-aware and could put that, that'd be awesome. So maybe it's a limb, right? It should be like, I don't know. I don't think they don't go for memes. Only I do that. So what word do we put between these? What words do we put between these? What goes between weapon and injury site, or site of injury and weapon are what of each other? What word goes between, and this is what we should know in the chi-squared test of independence. Every time we do it, we say that these two things are what of each other. We just say, well, the null is that they're just blank of each other. Independent, Kirsten, great job right there. We say that the two are independent, and then the alternative will be that they're not independent. So that's all we do. Now we have right here the expected values, and that's what expected cell counts are the expected values according to the null hypothesis. Thank you so much, Josephine. And so this right here is the same sort of steps we did just a moment ago. We're going to take and we're going to copy this table into, we could find this out, like you can solve each one of these. So it's important to know for the test. Let me just show you one by hand, because I fear sometimes people might watch these videos and not practice doing any by hand. Go ahead and solve, let's say, I'm going to put this in the chat. Solve the expected cell count for body / arrow. And then, okay. So solve that. And here I'll write the formulas, and I got a second question ready to go. So the formula for this is row total times column total over grand total. So that's the row total for it, and that's the expected. And I'll show that formula right here. And then we got another one, which is observed minus expected. This is the second question I'm going to ask. And that is a cell chi-squared. So could you do the one? Yeah, let's do that. We'll do that one next year, Maddie. I think we got just enough time. How do we get this? How do we get this expected? So I've got a question in the tower now. Solve the expected cell count for body arrow. So what is the formula for that? So how can we get the expected cell count for body arrow? So this is a really good test question. Like if you can solve these like that and know, and you will get these formulas on the test. So there's the formula row total times column total over grand total. So what is the expected cell count for body arrow? You can solve these all out by hand. Like, I'm going to use jump here in a second, and it's important to know like how to solve them, because you'd be like, I'd hate for someone to be like, well, Brian uses jump, so why are we expected to do these? It's like, we can do by hand. Like, we should know how they're solved for. Jump just makes it quicker for us. So body arrow, I'll give you some hints. There's body. There's arrow. Great job right there, Charlie. Yep, Charlie right there solving the mathematics for us. You just cross in on the 2. And this is going to get us the expected cell count of this right here. And so there we go. And Charlie, we will actually be doing some of this in 320. Not joking, we actually do this, but with permutations. So we use this exact same sort of idea, like talking about associations. And yeah, like, so if you're practicing this right now, you're preparing for 320. So when you do 320, you'll be like, this is easy. I got this. My old phone is being weird. I have no idea what the phone's saying on it. Each of these tests in the chapter uses the, it's probably chi-squared. Each of these tests in this chapter are used on the blank data. I don't know what the categorical, I think. Categorical. Do we always use the Pearson chi-squared in the p-value? Yep, we're always doing the Pearson test. There's the, what is the other one? Likelihood ratio test. We don't do the likelihood. If you look at the jump output, it shows likelihood. But I would say the Pearson has your p-value. The Pearson has your p-value. So people just showed the formula here. Now that we have that formula, let's go ahead and show how to get this in jump right here. So we're going to take the data. We're going to go right here. We're going to copy to clipboard. We're going to hit Control or Command C. It's all categorical, all categorical. Everything here is categories of weapon, category of injury site, and that is the condition of count data, that they're both categorical. We're going to go here to File, New Data Table to get a new data table open. And then we're going to go ahead and full screen it, or not full screen it. Let's go ahead and full screen it. And when we full screen it, let's go ahead and edit paste with column names. Very important. Make sure you paste with column names. If you don't, it'll look incorrectly. And we want to make sure we do that. Paste with column names. Now we're going to go here to tables and go here to stack, tables, stack. And we're going to double click all the blue ones. We're just going to stack them on top of each other. It just takes them all and just stacks them all on top of each other. Oh, did I miss one? It's going to cause a bit of an issue. I think I need to put them in order. There we go. Okay, now that we have everything right here, I'm going to call this weapon. I didn't change them last time. And let's go to site. Okay, there we go. You don't have to do that, but let's go to analyze fit y by x. We want to see if the weapon can explain the site of the injury. And let's go here to the frequency here. Now, it's very important you put the data in the frequency. That's the counts of the data. So let's go ahead and click OK and look at what we have. We have our full table of data. Now, one thing you run into is they sometimes change the order of these. But let's go ahead here and click the red arrow, and we can get those expected cell counts. It will solve them for us. There's that 5.5 we just solved a moment ago. If you remember just from a moment ago, we got that 5.5. And then we can also get the cell chi-squareds. So it's going to solve out the cell chi-squareds. That cell chi-squared of 0.455 is the observed minus the expected squared. So let's do that. Observed minus expected squared over expected. And there it is right there. That is that same number. Make sure you can solve for these. Once again, that was observed minus expected squared. And they call the observed the count. So, could you solve for this cell chi-squared right here? It's the cell chi-squared because it's right here. And this would be observed minus expected. Observed minus expected. Square that, and then divide by the expected. And you should get that number right there. So try to solve those. Make sure you can get them. Let's go ahead and take this picture of this. And here we go. I was shocked. Do we still have as many people watching? We have 24 people watching. That is crazy to me. Thank you for anyone just watching. If you're just chilling out right now, that's awesome. Yeah, wow. We're just knocking out some homework. So make sure they're in the right order. I've seen it sometimes where, arrow. Oh, this is the one that has an error. Look at this. It has limb right here. My Pearson, what are you doing? My Pearson does not get a 100 on this. That's supposed to be sword right there. And these are the expected values. So let me go and put this right here and put this right here. And body, so 5.5, 3.39, 2.11. It says 2 decimals, good. 5, 3.08. Make sure it's in the right order. Injury site, head, neck. Okay, good. Limb, body. It's very easy. Oh, and I did put I felt that. And 1.92. There we go. I think we got it. Awesome. Weapon equals limb. I will attack you. I mean, limbs can be weapons, but I mean, so the chi-squared death statistic. I know we need to tell my Pearson, like, hey, you didn't put something correctly on here. The chi-squared test statistic is your Pearson one. The Pearson has your p-value. So 8.19. And so 8.19 is the chi-squared test statistic. If you've missed it from the other ones we've talked about, that is the sum of all the cell chi-squareds. So all of these cell chi-squareds down here on the bottom sum up to 8.19. And the degrees of freedom, pretend you can't see it. How many degrees of freedom are there on this? Brian, this is a what by what? The degrees of freedom are what by what? These are the easiest questions, the ones we should know instantaneously, because Brian, this is a what by what? The degrees of freedom are then what by what? Practice this one right here. This is the one where I hate it when people miss points. I'm like, no! We have to be able to ace the degrees of freedom. Brian, this is a what by what? The degrees of freedom are blank by blank. 4 degrees of freedom. Great job, Leslie, right there, because it's a 3 by 3. So 2 times 2, 4 degrees of freedom. You're exactly right. So it's a 3 by 3. Also, do not be tricked if you see a table with more numbers. Only look at the groups like 1, 2, 3, 1, 2, 3. Don't use the totals. Don't use the totals. That's the most common mistake of people who know how to do this. They use the totals and they say, oh, that's a 4 by 4. No, 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 no. That's a 3 by 3. Don't use the total columns. So it's a 3 by 3 because there's 3 groups. 1, 2, 3 group. 1, 2, 3 group. 2 times 2. Boom. Charlie, Iris. Great job, Iris, right there. 4 degrees of freedom. That's going to tell us which chi-squared we are using. So technically, that 8.19, we would need to go to a chi-squared applet. Mubot, you are no longer blocked in the chat, Mublat. So we go to 4 degrees of freedom. We go to 8.19, and we graph to the right, and it gives us a p-value of 0.085. So we should be all right with that. We could look at the jump output. Jump's going to tell us the answer also, and the p-value is 0.085 right there. So the Pearson has your p-value. 3 decimals, yep. There we go. Should we reject the null at the 0.05 level? What do people think? Yes or no? Reject the null? Yes, reject the null. No, don't reject the null. Which would be fail to reject if we don't reject. Our p-value is 0.05, 0.85, 0.085. Either way. It's 0.85 or 0.085. It's either way. I mean, 0.85 is ridiculously high, but 0.085 is still high. So the p-value here is higher than alpha. When the p-value is high, just let it fly. Just let it be. We're going to fail to reject. We do not conclude that they are... Yeah. So we do not conclude that they are not independent. We do... I hate the way it writes it sometimes, but it's saying... Basically, this says we fail to reject the null. We do not have evidence for the alternative. So we do not have evidence to conclude that for the alternative that they are not independent. So literally this just says we fail to reject the null. We do not conclude the alternative is true. Like, we're not saying the alternative is true, but we're saying, we believe the alternative. And we're not saying that because we don't have enough evidence. So we should get everything right. Oh my gosh, what happened here? It's not that one. Did I seriously get one of these wrong up here? Are independent, non-independent. What happened? Well, it's not going to be that. Wait. It can't be this. It's got to be my, it's got to be these. Let me check these right here. What did I do? We had a streak going and I broke the streak. Arrow, body, head, neck, limb. You know what we do? We'll take this down to this right here. So sad, everybody. We had the streak going. Whoa. Oh my gosh. Wow, Brian can't copy numbers is what we learned. Brian can't copy numbers. How did I do that? What numbers did I put in there? Did I put the cell chi-squareds? Ooh, look at that. I put the cell chi-squareds along that. That's what I did. 38.53. I don't know how to copy numbers. 60. I should have noticed that these expecteds were really small. What should Brian have noticed? Like, if Brian was paying more attention, he would have noticed that. And is that other expected supposed to be that small? Because we do have an issue with the expecteds. 2.11, 3.39, 5.5. Okay, this should be correct now. You're welcome. Great job, Lauren, right there. Don't be like Brian. Don't miscopy numbers. Don't get your numbers wrong. Know how to copy numbers. That's a very important skill, is knowing how to copy numbers. We just have to have one mistake. That's our goal every day, to have one mistake, just to show you it's okay to make mistakes. It's okay to miscopy numbers. It happens. I was like, none of these multiple choice right here, I feel, are wrong. Is there another one? We have just enough time for one more. I'm trying to see if we have a shorter one. Got sunken treasure. Let's do these right here. Great job, Lauren. Let's do these right here. Let's do multiple choice and we'll end office hours. Pregnancy question. Yeah, did we do the pregnancy one yet? How does it start? How long they are? What? Can you copy the start of the question for me? Copy the very start of it. Standardized residuals are basically like when you see how much you miss by and you standardize by the amount. Don't worry though, it's just asking about this. The only question you missed, email me, Lauren, and I'll fix it, because it's confusing, but it's just asking about, is the expected cell counts greater than 5? Most pregnancies are full term. Awesome. Let me pull that one up right here. I'll just fix that one for you. It's, since, you know, it's a little bit, here we go, we got that question up. It's just asking, are the expected cell counts over the 5? And that's the issue with it. The standardized residuals are a little bit weird because the expected cell counts aren't greater than 5. So let's go ahead and take a look at Maddie's question right here. So once again, we have categorical data right here. And what do we put between these two right here? We just say they are independent, and the alternative will be that they're not independent. That's something we like to practice a lot right here, is we always say that the null is that they're independent, and the alternative is that they are not independent. So know that instantaneously. You're welcome, Lauren. So now we get down to, what is the chi-square test statistic? But you know what? I like the question below this even better. The question below this asks the p-value. It asks the p-value. I thought it was degrees of freedom. Dang it. What would the degrees of freedom be on this? Who knows the degrees of freedom for this table up there up top? We'll get the chi-square test statistic in a moment. But who knows the p-value right here? The degrees of freedom are going to be not 1. They're going to be 3. So, Brian, this is a 2 by 4. 1 times 3. 3 degrees of freedom. Does that make sense, Maddie? Yeah, don't worry. It's just practice. We always say just practice. Let's throw some 50 points out there. Great job, Leslie. Great job, everybody. It's 3 degrees of freedom because it's a 2 by 4 times 1 times 3. Great job, Cliff. And those are the ones we just, like, after you practice it a whole bunch, you're like, okay, bam, got it. And let's go over here to jump. Let's go to File, New, and then let's go to Data Table, File, New Data Table. And let's go to Edit, Paste with Column Names. Now we have everything right here. Let's go to Age Group. And there we go. Let's go to Analyze. Let's go to Table. Let's go to Stack. And this is the major important part. Please slow me down or stop the video. Make sure you see this part. When you go to Table Stack, stack the blue columns right here. With the blue columns stacked, we're just going to go ahead and click OK. And make sure you have everything that looks like this. Make sure you have everything that looks like this. So now that we have everything that looks like this, we have length. Let's go to length. And yes, I just double click it to change the name of it. If you double click it, it'll change the name. There we go. And so we have everything looking good. Let's go here to Analyze, Fit Y by X. Analyze, Fit Y by X. You're going to go ahead and see if the length of the pregnancy can be explained by the age group. And more importantly, you have to put the data down here in the frequency. So let's go ahead and put the data in the frequency. And then we have, does the length of pregnancy, is it explained by the age group? And what do we have? And look, does this look to be independent or not independent? What do people think? Looking at this right here, what do you think? Independent or not independent? Just like if you look at that and be like, okay, these are the younger people, like the under 20, the over 40, and if they're late term or if they're early term. So does that look independent or not independent? If I'm looking across this right here, it looks like all the age groups are very similar. And so the p-value is going to be pretty high. Yep. So if you look down here, you see a chi-squared test statistic of 1.829 and the p-value right there. So that's got it. Sorry, everyone. So Stat Nation is back. Keaton, so good to see you. Keaton, were you in the mini term? About to have mini term again, and mini term is the one that made up Stat Nation. I like to tell students I didn't come up with it. Students started calling themselves Stat Nation, and I went with it. So we're 100% Stat Nation. So Kinga, so good to see you, Kinga. Love seeing like everyone in the chat. It's so good. The p-value right here is 0.6086, 3 decimals, 0.609. So, and then May 2020. Yes, Keaton, that's so awesome. We got so many new things. We got Puppet Shark now. Puppet Shark, you need to be louder. This tiny Puppet Shark.
We even got Tiny Brian.
There's a lot more additions right here. Newspaper headlines. I think we might not be able. Let me see if we might not have enough time, Kirsten, but we will be back. Let's see right here. Are we going to reject the null or not reject the null? Our p-value is ridiculously high. So what do you think we're going to do? The p-value is greater than the level of significance. There's not evidence to reject the null, or there's not reason to reject the null and conclude there's evidence for the alternative. Everyone loves Tiny Brian right there. Oh my gosh, we're back to getting 100s. No more errors for us right here. We fail to reject the null. There's not evidence to the alternative. We do not reject the null exactly. Our p-value is way higher than alpha. This p-value right here is way above alpha. We do not have enough evidence to reject the null. And if you look at this graphic, just when you look at it, visually speaking, it just looks like they're independent of each other. It's like, okay, someone's age group is independent of how long their pregnancy is. Like, it doesn't really give you any information to know what age group someone is in. It's all, stop all here. Stop all the downloading. Hey kid, I'm a computer. Oh. I think we might have to come back and do that other, the next one. Kirsten, we might have to do that next one. Should we speedrun this question? How quickly do people think I can speedrun a question? Let's get this question up for a speedrun. We don't do, and so yeah, we don't do nearly enough speedruns. Okay, here we go. Brian's going to try to speedrun a question. Let's make this happen right here. I'm getting the screen ready for the speedrun. Okay, let's do this. Time for a speedrun. Okay, so we're going to do this right here. Got the speedrun screen up and going. Okay, trying to get this. I was trying to get this screen like optimized. I can't see the screen until we get to it. Let's go. This is my last semester. Oh, exactly. Mini-term is really great, Keaton. I agree. Like, you have to stay on top of the work. You have to be like following along, doing all the work. So you have to be doing everything you can. Did we have this? I don't think we had this when you were in mini-term. The speedrun screen. Let me get a jump sheet up. I'm just getting all the prep work done. I'm allowed to do prep work to get my speedrun going right here. So that way the screen looks proper so you can see it all. Okay, we are good to go. Brian is good to speedrun this question. Let's make this happen. You ready? So here we go with one of the Stat 1 speedruns. Speedrun this question right here. Let's do it. Okay, the null hypothesis is that the two things are independent. So the first thing I'm going to look for here is that they are independent, and they're independent in association is what we have right here if they're not independent. So are the conditions met? Oh, those are big counts. So we do meet the expected cell count. Yes, because they are. The data groups are. Nope, we want them to be independent of each other, random, independent, and the groups have it. The groups have. Let me see here. Yes, the groups are sufficiently large. This should be expected. My Pearson, what are you saying? The expected should be greater than 5. Yes. So I think we're good right there. Everything's good. Calculate the test statistic. The chi-squared test statistic can be done by going over here, copying the data. This is a speed run. I will do this one later, more slowed down. We're going to go here to edit, paste with column names. Once we get it pasted with column names, we're going to go to, oh, we can't see that. So edit, paste with column names. Then we're going to go to table, and then we're going to go to stack. On table stack, we're going to click the blue columns. That'll stack them up. It'll open up in a new data sheet right here. So here's our new data sheet. We're just going to go right here to make this easier to read. We're going to go here to status. And then we're going to go here to gender. And then we're going to go and analyze fit y by x. We're going to put, does somebody's gender explain their status? And then we're going to put frequency right here. And here is the data. So we see here, yes, females were more likely to be alive. And the chi-squared test statistic is going to be 589.33 with a p-value of 0. So the chi-squared test statistic is 589.33, and the p-value is 0. And we definitely reject the null and conclude that there is strong evidence, and we've done it. That's got it, under 2 minutes. So we will come back. We will do this one more slowly. A lot of the same processes. If you watch this and you're like, Brian, I have no idea what just happened. Well, check out today's later office hours. We're going to do this one more slowly. I'll be teaching here in just 11 minutes, but we will do this one more slowly later. A lot of the same processes of copying the data into JUMP was done right here. So if you're watching the earlier parts of today's video, you can see how I copy data into JUMP, and then we find the chi-squared test statistic. You're welcome, Kirsten. Kirsten, were you able to solve it? Was this one yours, Kirsten? Kirsten, if you just solved it, amazing work. You notice the p-value here is super low. And then last but not least, when you look at the test right here, you can see our hop over to the main screen. You can see that there's a big difference. So yeah, awesome work. If you were able to solve this, awesome. See you very in class. It's so much. We're almost done. Let's put on a little 80s music right here. Oh my gosh. I think I just woke everyone up. I just woke myself up. Well, that's got it. So good to see you. See everybody right here. Keaton swinging by. I'm going to make some more coffee because I got to wake up some more. Woo! That's got it for now. We'll be back. Keaton, swing by anytime, man. So glad to hear you enjoyed the class. So glad to see people just swinging by. Today is the last class of stats. Let's go. Let's make it happen. I'll see everybody soon. Bye for now, everyone. Bye! I'll be back later. I can talk over the outro screen now.